So hi, I'm Alex, and I'm going to be shining a light on what I think is nature's worst kept secret. But first, a little on light. We as humans use light to see, plants use sunlight for photosynthesis, but as scientists we use light for spectroscopic means, to analyze compounds or matter. Today I'm going to be talking about using light and just simple optical physics to get information on energy storage devices, specifically their nanostructure. Now you may notice that my presentation slide's a little dark at the moment, but just like any good optical physicist, I'm going to shine some light on that. Now, when I'm talking about the nanostructure of these materials, what I'm actually referring to today are photonic crystals. And these are materials with a periodic, ordered structure that affect the flow of light. Some good examples in nature include peacock feathers and butterfly wings, where the bright colors we're seeing aren't as a result of some pigmentation or dye, but rather a nanostructured surface interfering with the light. Now, these bright, vibrant colors have been in front of our eyes, right under our noses for years, but it's only recently that we've come to understand the true applications of these structures, despite being one of nature's most obvious and worst kept secrets. Now, to give you an idea of the scale of these structures, if we wanted to cover a 1 by 1 centimeter surface with these nanopores, that would be the equivalent of trying to cover the entire floor of this lecture theater with the head of this pin. So I've done 2 here, just about 300 million more to go. When we talk about using these structures scientifically, what we're actually looking at is the light reflected from the surface. So when light is incident on this periodic ordered structure, a certain wavelength or color is reflected, depending on material properties. So the first property would be the size of the pores themselves. So if we turn on our first light, as the size of the pore increase, the wavelength of the reflected light gets longer, and vice versa. What also can change the color of the reflected light is the material filling the pores. So we can replace the air with a liquid, and that also changes the color. And then we can use this color reflected from the surface to give us information about the material properties and the material filling it. And that's great, but the true advantage of this type of approach comes from combining what we get optically with the battery process. So if we think of our current battery devices, some of the most common complaints are they take too long to charge, they have a short lifetime, and you need to charge them up every day. So to answer these questions in the future, we're going to need to look at more materials. And if we can force the materials to adopt this ordered structure, well then we can look at them in real time, quickly and efficiently. We can screen through potential materials, monitor them optically, and identify the best candidates, essentially giving us a non-destructive, non-invasive, real-time assessment of material performance that I think is going to be essential, meeting our future energy storage needs as we as a society move towards more energy-dependent devices and that are also flexible and wearable to suit consumer needs. Thank you.
Thank you, Alex. Lovely talk.